We have a lot of material to talk about, and I have a shocking few number of pictures. So this is more going to be more of a audio podcast than anything else. If you want to follow along, go to IMC Chapter 4, and we're going to talk about overload relays first. And I know you've all read this, so it shouldn't be anything new to you, but I want to go over some essential information. I've said before that there are certain fuses that you can use for both the overload protection and the branch circuit protection. And they're called dual element time delay fuses. Dual element time delay fuses. And you can sometimes protect the circuit and the motor with a dual element time delay fuse. But I think I've said this before, and I'm going to say it again, don't ever do that. Because if you fail to protect the motor, you fail to protect the motor, and you get to buy it. Most likely, if you're the contractor or the foreman, if the motor fails and you did not have motor overload protection for the motor, you're probably going to wind up paying for that motor, because there's going to be a big argument about, well, you didn't protect the motor, you only protected the branch circuit. And you can argue that the fuse should have protected it, but if you're at that point, it didn't protect it, and you're going to be on the hook for buying it. So, yes, that's true. Personally, as a point of reference, as a contractor and a foreman, I would never, ever do that, though. All you're saving is a set of a motor starter, and you probably need the control of the motor starter anyway, so there's not much sense in protecting the motor with just the fuses. If you do, well, I've said that already. So forewarned is it's forewarned. So take it for what it's worth, and there we go. So to do that, a dual element time delay fuse uses two parts. One part melts on extreme overloads, and that's the branch circuit protection. And then there's a solder piece and a spring that protects the motor on the motor overload portion. And generally speaking, we use dual element time delay fuses in motor control anyway, because we want that inrush current to go ahead and happen for a couple of seconds. Sometimes we need to let 6 to 8 times the full load amperage flow to the motor so that it will start. I mean, if it won't start, it's not going to do you any good, right? So you've got to allow that inrush to happen to get things going. And in allowing that, that's a big, say, a tsunami of electrical current. You know, it's not a tsunami, but it's a big wave of current that's going in. It's kind of rushing in. And as we talked about the induction of the motor building up and slowing down the current flow. So it only happens for a second or so, and we want to allow that dual element time delay fuses do that almost better than almost anything else. So we want to allow that. If you're using instantaneous fuses, you have to use much larger fuses, and it doesn't protect the circuit very well. Or if you're using instant trip circuit breakers, if you're going to be using that instant trip circuit breaker at 8 times the inrush current, 8 times the full load amperage, that inrush current is going to be 8 times the full load amperage. That's a lot, or it can be that much. Okay, let's talk about motor overloads. Motor overloads are what protect the motor from the continuous excessive current from drawing too much current. We've talked about, or maybe we haven't, that some motors cannot take any overload. Yeah, we have. We talked about that, didn't we? We talked about motors having a rating. Anybody remember what that is? If the rating is 1.0, you can't overload the motor at all. If it's 1.15, service factor, it's called service factor. It's on the nameplate. We talked last week about the nameplate, remember? We talked about having a service factor. Okay, motors that are stamped 1.0 service factor, that means you cannot overload that motor at all. Don't do it. And because of that, most of the overload heaters are set to shut the motor down right about 90% of its full load amperage. We don't want it going to full load amperage. We want it falling short of that, because if even a 90% is going to let it go past the 90% a little bit, right? We don't want it going much past that, because that motor will become damaged very quickly. Then there are motors that have a service factor of 1.15. That means generally you can overload them about 15%, even on a long-term basis. And it won't kill the motor. It won't shorten its life a great deal. What does that mean? It means they use a lot more copper making that motor. It costs a lot more money, right? And then there's the service factor motors that have a 1.15. A 1.25. That means you can overload them about 25% without killing them. And generally speaking, if you buy a motor that has a service factor of 1.25, it'll cost a lot more than a motor with a 1.0, because it's going to have a lot larger copper windings in the motor, in the windings of the motor. Okay, so a solder pot overload is a device that senses the heat, because the solder literally will melt at a very specific point of temperature, right? Very, very narrow band. And we take advantage of that by creating a device that will let a spring-loaded device open up when the solder melts. And that's why it's called a solder pot overload relay. And they're still in use almost everywhere, because they're inexpensive, they're accurate, they're reliable, they're just good at what they do. If you look on page 37 of IMC, in the bottom half of the page, you see the solder pot overload relay. Now, we've talked about this picture before, in that we were talking about a mechanical starter, remember? And we said that it's only slightly different in the overload section, because it doesn't have an electrical contact in a mechanical in a mechanical overload. Okay. Now, there are bimetallic strip devices that work more or less the same way, but slightly differently. They have two strips of metal bonded together, and they move, and they create a little movement by overheating, and they move a latch that's spring-loaded and opens up. Then there are magnetic overloads that kind of do the same thing when a certain amount of heat is created by the magnetic field, or it's not the heat, it's the magnetic field is large enough. It's assuming that amount of current is an overload. So it's kind of not really sensing the heat, which is not really what we want to do. We really want to sense the heat that's happening, because heat is the enemy of every motor. Okay. Our book talks about dashpot overload relays. And dashpot overload relays are sometimes used for starting a motor to create or allow the inrush current to happen before some other heat sensing device kicks in. Also, they can be used as just a timing device, because they're just creating a time delay from when it started to when the contacts are closed. The overload contacts in that overload heater we looked at on page, 37? The overload contacts, very often, they only have one overload contact. In the modern ones, there'll be 3 overload heaters and 1 overload contact. In some of the older ones, it's 3 overload heaters and 3 overload contacts. And that's okay, but if you see the 3, you know that they've got to be wired in series, so if one drops out, they all drop out. Drops out the control circuit. Okay, in protecting a large motor, often we'll use a current transformer to step down the current so it's not quite as dangerous, to sense it and evaluate the overload of it. And now let's move on to relays, contactors, and motor starters, which is really getting into where we live as an electrician. You know that every relay is an electromagnetic device that has a coil and a plunger. The electromagnetic force pulls in the plunger, closes contacts or open contacts. They change state. Some some magnetic relays have a shading coil. And the reason they have a shading coil is to remember that AC voltage drops to 0 120 times a second. So some devices will have enough delay that that's okay, and some need to add a shading pole for that. All right, so this is the overload device, solder pot overload device, same one that's on page 37 or whatever page that is. And I want to go on to talk about solenoids, relays, contactors, and motor starters. Those are all different things. All of them are electromagnetically operated. And you know what? Hang on one second. Okay, when we start talking about relays, lighting relays, solenoids, contactors, motor starters, they all have one thing in common, is that they're electromagnetically operated, and that because of that we can control them remotely. Here we have a picture of what we call a solenoid from a car. Now, it's not truly a solenoid. Actually, it's a single contact relay because it has electrical contacts, but somehow all the car companies call them a solenoid. Well, it's just not true because it's moving a set of electrical contacts, so it is a relay. So this, you see the 2 small terminals and the 2 large terminals. The 2 large terminals are copper. That's because they're the big current terminals, and the little ones are the small current terminals, meaning that the control circuit goes up through your key switch. You don't want 100 amp wires going up through your key switch, do you? If they develop a short, it probably might be a really bad thing. Having a 100 amp short through your steering wheel might be a very bad day. So what we have is we have control circuit and power circuit. Even though there's only one circuit each, that's all there is. Now, what would we have if we had a real solenoid? A solenoid has no electrical contacts. We would have 2 small contacts, all right, to pull in the plunger, but when the plunger went up, it might do something like open a sprinkler valve or push some physical thing or release a latch or something, but it's not going to have electrical contact. So if I say solenoid, you know that it's not moving electrical contacts. We have solenoid braking. You know, the new cars are coming out with that really trick braking system. It could be solenoid braking. It's not, but it could be. It could be pulling in the brakes physically with a solenoid. Okay, the next kind of thing we want to talk about is just a simple contactor. Now, when we say simple contactor, that relay that you start your car with is a simple contactor, right? It's a simple relay. Well, that's true, but a contactor generally refers to where we have a lot of contacts. You'll notice that we just have, what is it, 7 sets of contacts, 14 sets of contacts. There's no holding contact. There's no, or is there? This might have a holding contact, but it's still just a lighting contactor, because what do we not see on this thing? Overload relays. It's not intended for motor use, right? This is for maybe parking lot lights where you want to turn on 7 circuits or 14 circuits of lights, and you want them turned on all at once, like when it gets dark. Okay? So this is a lighting contactor. Lighting contactors are very often mechanically held. Once they're pulled in by the on relay, they have to be released. You have to have a latch that's released and let them spring load open, or there's a physical push them open relay, or plunger I should say. So mechanically held, fairly often, lighting contactors are mechanically operated. They're a relay to turn them on, a relay to turn them off, and they serve a very special purpose, turning something on, leaving it on for a long time, turning it off. Okay? All right, now we have our standard motor starter, and you can see here at the top that we have the coil, and it can be any voltage. You can have a coil for whatever voltage you're using to control the circuit with, and these they're completely separate from the power contacts. The power contacts come in here, here, and here, and leave here, here, and here. And you notice that we have a overload block down here, an overload relay. And so in there's going to be a normally closed overload contact that breaks the control circuit. And over here on the left, you can probably see where we actually have the wires for the holding contact over here, and they should be marked 2 and 3. One of the things that happens with a lot of starters is that they'll chatter. And any relay can chatter because, again, the circuit goes to 0 120 times a second. So you might hear a very distinctive and that's the chatter of the circuit, the coil being shaken in and out 240 times a second. So often we'll have a shading coil, almost always, and that shading coil is just a little metallic ring that goes around the other windings to create a secondary magnetic field in that ring. And what that does is that it will have a second magnetic field. And what it does is a very weak pull, but it pulls when the other circuit has gone dead. When the main magnetic field has collapsed, it will create a little pull. So it keeps it pulled in all the time. You notice this particular one has a shading ring or shading coil on both sides. And that's a very important thing. In the lab, we're going to take a motor starter apart. You're going to have to pull apart the plunger and the coil and look at the 2 parts of the coil. There are 2 parts. And one of them will have a shading coil or 2. And you'll need to identify that. So what identifies a motor starter from everything else is it not only has a holding contact, but it also has overloads. And if you're going to do a motor setup, include a motor starter with a heater, because if you don't and it burns up, it's all your fault. Okay. Some other control relays we should talk about are the smaller type relays, and they plug into this little block. They're called ice cube relays. They're very small. They're for control circuits only, and they do things like turn a circuit on, turn a circuit off, pull it, have a little timing. There is a time delay relay that will go into a 8-pin or 11-pin relay. And there's something I do expect you to know about both of these. Okay, I want you to look at where the pins for the coil go in here. And notice that on this one, this is an 8-pin, and it goes in the second pin. And now look at this. It's 1, 2, 3, 4, 5, 6, 7, 8. You see that? So it's on 2 and 8. I mean 2 and 7, sorry. It's on 2 and 7. It's on the second and second to the last. So that means if we looked at a picture of an 11-pin relay, we would expect the coil to be on 2, and the second to the last on 11-pin would be 10. So our coil would be across 2 and 10 on 11-pin relay. So the second pin and the second to the last pin are where the coil is. And yes, I expect you to remember that from now on. All right, simple stuff. So anytime you have a block, usually they have markings on what everything is. You notice on this one, we have a common pin, which is 1, and another common pin, which is what? 11. No, this is 8. Sorry, this is an 8-pin. So it's the first and the last are the common pins for the normally open, normally closed. And you notice that we have a normally closed up here on 4 and 5. And we have normally open on 3 and 6. So 8 pins are always laid out like this. So even if the diagram is not on the little block, not on the relay, not anywhere, you should still be able to figure this thing out. Remember that 1 and 8 are going to be the common pins on, and how many sets of contacts does this thing have? It's got 2 sets of contacts. How about an 11-pin? It can have either 3 sets, or it can have some other things in the middle instead of another set of contacts. Like you can have a normally open switch that starts a time delay. Or you can have, in other words, it's kind of the middle set of an 11-pin are often used for other times. And then you have to break down and read the instructions. I know that's counterintuitive to most of us, but that's okay. Sometimes you got to do that. Okay. Let me stop this for a second. All right, so now we're going to talk about motor starters. And we're going to talk about sizing motor starters. And motor starters are sized by the horsepower of the motor you're starting. They're sized by the horsepower, primarily by the horsepower. Now there are 2 kinds, NEMA and IEC. NEMA stands for National Electrical Manufacturers Association, and IEC is an acronym for International Electrotechnical Commission. In other words, European. Now, there is a major difference between the 2. NEMA is American made, and they're very heavy duty. They will very seldom burn up. Very seldom. If you size them correctly, generally speaking, they will live forever. Now, I shouldn't disparage using an IEC starter, but I'm going to, in spite of the fact that that's probably not the right thing to do. But my experience in the field has shown that even if you select the exact right IEC starter, it may not live for very long. They're built very precisely, and if the very slightest overload is in it for any long period of time, they have a tendency to not work very well. So there are the two different kinds, and I'm just in the habit of never ever using an IEC unless the customer absolutely insists. And then I'm going to make him sign a piece of paper that says, you specified this starter, and I have no faith in it. You will be buying it if it burns up. I will not be responsible for this starter. That's all there is to it. So that's just a personal prejudice, and I shouldn't pass that on, but that stuff is somewhat delicate, in my opinion, and I don't even like delicate cell phones. I like the ones that are, you buy the military grade cell phone and you can drop it from 3 feet. And same thing with computers. If I'm going to carry it around, delicate's not a good thing. So same thing with starters. If I'm going to work with it, I'm not liking delicate. So it's just my personal preference, and you certainly don't have to follow that. There's a motor starter selection chart in our book. You're going to be getting an overload device selection chart sometime soon. And the front page will be this page right here on page 69. And it says NEMA size, and then it says the voltage of the load, then it says single phase or polyphase, and then it gives the horsepower. So they go down all the way to half horsepower single phase motors, and they go all the way up to 3-phase 575 volt 900 horsepower motors. That's a big motor. So if you're using a size 8 starter, that's one big motor. Okay. Now the smallest one is not 00. Don't go in the wholesale house and say, I would like a 00 motor starter. No, you want a double aught. A double aught motor starter is the smallest size by NEMA standard. Single aught or 1 aught is the next larger one, and larger than that is 1. And you'll notice in NEMA there's a 1P. What is a 1P? It's for a single phase. And why is there a 1P? Because it's single phase only, and it's a little more than 3 horsepower. It'll go up to 5 horsepower in single phase 120. Now, generally speaking, you're not going to do that. If it's over 2 horsepower, you don't want it 120 volts. Okay, if it's more than 1 horsepower, you don't even want it 120 volts. You want it 230 volts, or 240, whatever you want to say. And why is that? Keep the current down, lower current, lower voltage drop, lower inrush, lower everything. All right. Now there's some things in here you need to learn just by looking at this chart, and some of that you can't do by just looking at the chart. We're going to do a couple of selections. If we were going to have a 40 horsepower motor, and we're going to operate it on 480 volts or 460 volts, what size starter would we need? We could probably, at 480 volts, we could use a size 3, because look at polyphase. We're assuming it's polyphase. And in 480, 3 goes all the way up to 50 horsepower. Okay? And a lot of times you would think, no, I've got to go up to a size 4. No, that's if it's at 200 volts, like 208. That would not be the right starter if you're operating at 240. So it's very voltage dependent. Why is that? The amount of current that's going in is dependent on the voltage, because it's the power you're putting in divided by the voltage will be the current, right? So the higher the current, let me rephrase that. The higher the voltage, the lower the current will be. So you have to take that in consideration when you're selecting these starters. And we're going to start doing this pretty soon. Because what did I say at the beginning of the semester? That one of the main things you're going to do here is you're going to learn that if some owner comes in and puts 4 motors in this room, you're going to sit down and start making a material list of everything you need to connect these motors and get them running, right? Well, the first thing you have to do is select the motor starters, right? So using this chart is going to be an essential skill. Okay, so this is going to be the top page of your motor overload heater element selector guide, which I'm going to give you soon. And then we're going to start working out of that. So look that chart over on page 69 fairly thoroughly. If you believe you'll be working in Europe or someplace where they use IEC more often, you might want to look at page 71, the IEC motor starter selection guide. You know, notice there's a lot more of them. You might say that they're more narrowly sized. Okay. All right, one last thing I want to talk about today is the control transformer. Okay, the main thing you need to know about a control transformer is that they're all dual voltage transformers. But they only operate on 2 voltages, 240 and 480. That's the supply voltage. What comes out the bottom end is 120 volts every single time because you're putting in the 240 or the 480 in the proper way. In the top, we can do this because we have 2 sets of windings in the top of the transformer. And so if we have a higher voltage, how would we hook up the 2 windings so that we have the same voltage drop across both sides? No, in series. We're going to connect them in series so that we have, what are we going to drop across this winding? If we connect this in series, if we tie H2 and 3 together and put 480 across H1 and H4, we'll put 240 across each one of these 2 windings right here, right? Series circuits are voltage dividers, right? So we want to have this 480 connected in series, so we put 240 across each winding on the top side, and it's a 2-to-1 step down, so we're going to get 120 out of the bottom, right? So if we want to get 120 also, and we want to supply 240, if we're going to supply 240, we're going to have to bring 240 both to this winding and to this winding, so we're going to have to put a jumper between here and here. And we're going to have the other side of our 240 come to here, and we'll put a jumper between here and here. Now we have 120 across here, 240 across here going out. And we have 240 coming in from the other side and going across here and going out. So we have 240 across both windings still. And we'll still have 120 coming out. Now what we do with that is whenever we have this, we will always fuse one side and ground the other. So let's say we're going to fuse this side. The other side we'll take to a ground also, so we have a grounded 120 volt system. So then we'll take our control circuit from those 2 points right there. So remember, we're going to fuse one side because this being fed by what? The top side of our motor starter. There's no fuse there, right? Except the motor branch circuit. And that's the motor circuit might be fused at 100 amps, 150 amps, 200 amps, 400 amps, 800 amps. essentially it's unfused. So we can protect this transformer by putting a fuse on the output. Now that means that the wires coming to it might be unfused. A lot of people put a fuse as soon as they come off the supply side and fuse it before they get down to the transformer so that it's safer to work on. I only know a few actually, but that's a whole different Oprah. All right. So now you know how to hook up a control transformer, right? If it's high voltage, you hook it up series. If it's low voltage, you hook it up parallel. Mighty fine. Okay. I think that's about it. I think that's all I need to talk about today, at least, anyway. So remember, this is your control circuit that's coming off this control transformer. Now there are three, let me throw out one more thing that you need to know for the lab, this class also, I guess, and that there are three different kinds of control strategy supplies, or control supply strategies. One is called common control. That's where you take whatever voltage you have on line A and line B, and you use that to control your circuit. Your control circuit might be at 277, 480 if you do common control, right? How many people want to have 277, 480 on their control circuit? Even if it's fused so that you can only get a few amps. That's probably not going to be any fun if you touch it and you're touching something grounded. Probably not anybody's favorite. So that is going away in general as a control method. That does not mean you will not see it in the field. You will find that in the field fairly often. You'll find common control, and it's not a very safe situation, but you may have to work on it anyway. Okay? Then we have, of course, control transformer supplied control circuits, which are all very safe. And then we have what's called separate control, and that's where we take, say, a 120 volt lighting circuit. When we bring it into our control panel or our starter circuit, and we use that 120 volt independent circuit. Now it's fused from someplace else, completely different. So you might have your power off, but you might have a live control circuit. So you've got to be careful with that also. The one most safe, in my opinion, is the control transformer. And if I get to choose how this thing's going to be installed, and usually I'm going to get to choose, I'm going to select one with a control transformer. I don't want a different circuit in there because I've got to remember to go turn off that light circuit to make sure that my control circuit is dead when I go to troubleshoot it. If I put my ohm meter on a 120 volt lighting circuit, what will happen to my meter? It might let all the smoke out. And that's my meter, or at least it's the one assigned to me. And now that it's blown, I've got to go get a fuse. Now I'm not very happy. Okay, so all of them have some kind of drawback, except, well, even control transformer, because it's got its own drawbacks, but in my opinion, that's the best way to do it. All right, we're going to close this recording for the day and start again another day.